Okay, so when we left off here in the last video, we were talking about how we can get a precise number for the area underneath the derivative by increasing the number of rectangles we're using to estimate it to infinity. So taking the limit of the area expression as the number of rectangles goes to infinity. And then at the very end, I did a little example using the integral operator to find the area under the line 2x. So in this presentation, we're going to talk a little bit more about how do you actually find an integral that's not linear and all that good stuff. But before we get started, I just want to do a little vocabulary. So far this year, if we had a function, f of x, I'm going to make it capital F for a reason that'll be apparent here in a second. Let's say this was 3x cubed minus 6x squared plus 3. And then we take the derivative, we get little f. The derivatives would be 9x squared minus 12x. And that's it. So when we have done that, we have said that f prime is the derivative of f, and then anytime we've referred back to this function, we've called it the quote-unquote the original function. And so that's worked fine because in a lot of problems we were given this as the original function, like that's what was given in the problem, and then we had to find a derivative. And like all of the problems we're about to do now, we're going to be given a derivative and we're going to have to reconstruct this function. And so it doesn't make sense to call it the original one because this is will originally be given the derivative, blah, blah, blah. So anyway, for vocabulary, if we are given a derivative of a function, so a lot of times that'll be notated with the lowercase letter, the quote-unquote original function, or what we've been referring to the original function, will often be referred to as the antiderivative. I know, it sounds so sci-fi. So this is just a more mathy name and more specific name that we need to use for the original function. So if we are given a derivative and we work backwards to find the function for which the given function is the derivative, that is the antiderivative of little f. So the antiderivative of f prime is just f. And so part of what we're going to be working on in this presentation is how do you find the antiderivative of a given derivative. It is at least as much fun as it sounds. Don't worry. Okay, so let's start with just some examples. Where we left off. So before we jump into examples, we do need to talk about the fundamental theorem of calculus. Okay, so what we saw in the last video was if we have a function and we want to find the area, and we want to find the exact area, we set up a sum. We're adding up the area of a bunch of rectangles. We take the limit as the width of each rectangle goes to 0, and we have an infinite number of rectangles, and that is what an integral means. So we left off with that shorthand and that notation. So the integral from a to b of subfunction f of x gives us the area underneath that function. So the bummer about all that is that this side of the equation is just like a huge pain to deal with. It's very complicated. It depends on having to find some tricky substitution to do, It's just kind of a bummer. But as we talked about last week, we can also attack this problem from a different perspective. So we talked about last week how if we are finding the area underneath a rate function or a derivative, intuitively, that tells us that has to be equal to the net change in the antiderivative of that function, or what we refer to as the original function. So the example we looked at a lot last week was if we have a velocity function. If we find the area underneath the velocity function, that tells us the net change in position being the antiderivative of velocity. So this fact, that the area underneath a derivative So so this side of the equation is the area underneath the derivative in between a and b is equal to the net change from a to b in the original also known as the antiderivative. This is called the fundamental theorem of calculus. It's like super important because what it's going to allow us to do is to get around having to find this gross sum. Because if we can figure out what the antiderivative of little f is, then we can just evaluate the antiderivative at b and a, and that will tell us what the area underneath the given derivative is without having to compute this like crazy sum. So we are now shifting the problem. Instead of trying to figure out how do I evaluate some big sum, the challenge of these problems is going to be, can I figure out what is the antiderivative of the function you've given me? And to put it more casually, like, what function is this the derivative of? And this is why it's like so crucial to be so familiar with derivative rules, because now you're going to be looking at a function and you're going to have to work backwards from what we've been doing so far this year. You have to look at something and be like, okay, can I reconstruct the process that created this derivative? Like, if I look at this, can I figure out what the antiderivative was that would give me this derivative? Because that's how we're going to figure out these guys over here to answer these questions. So let's just start looking at some really basic examples. So let's say that the function that we are trying to find the derivative of is just f of 5. And so what is the antiderivative of 5? So you need to think of what function did I take the derivative of that gave me 5? Okay, so I'll let you think about that for a second. And, one answer to this is 5x. Is this the only option? Can you think of a different function that also has a derivative of 5? The answer is yes. There's actually an infinite number of potential antiderivatives. 5x plus 1, 5x plus 1,234, 5x minus 29. So since constants disappear when you take the derivative, when we are just trying to find an antiderivative, there's actually an infinite number of solutions. And that group of functions that are potential antiderivatives are called a family of functions. So a group of functions that all yield the same derivative, that's a family of functions. So a lot of times when we are trying to find an antiderivative in general, we'll write the solution to this as capital F, and so that's another convention. A lot of times the capital letter stands for the antiderivative, is 5x plus c. And this c will be called, is called the constant of integration. And it's just there to stand for the fact that there's an infinite number of functions that can be the antiderivative of f of x equals 5. As long as there's a 5x plus any number, that is a solution to the question we were being asked. So the integral of 5 dx is 5x plus c. Okay, that's on the next slide. How convenient. Okay, so let's look at a slightly more complicated example. So let's say we have a constant. So there are some examples down here. So the general rule is that if you're integrating a constant, excuse me, scratch your throat. You just slap the variable on it and add a constant of integration. A couple things to notice here. The one thing this d term does tell you is what the name of the variable is. So here, since I'm just integrating 3, I don't know what variable. It doesn't appear in the given problem. So the fact that this is dx tells me that the variable I need to use x. Here, because of dt, I know the variable I need to use is t. Another note about this one here. I've noticed in the past that sometimes students get confused if they have an integral of just dr. You can think about that as the integral of 1 times dr. And then when you integrate 1, you just get the variable. Sometimes when people see the integral of just, let's say, dx, they're not sure how to integrate that. It's just going to be x, so 1x plus c. Excuse me, sorry. Okay, so what if what you are trying to integrate is not a constant, but is just a power function? So here we're going to be doing the power rule in reverse. So if you remember, the power rule was the easiest derivative rule. If we have some function f of x equal to x to the n, its derivative is n times x to the n minus 1. You bring down the exponent and reduce it by 1. So now we're going to be working in reverse. So if I'm trying to find the antiderivative of f of x, so I'm trying to do the integral of x dx, I'm trying to ask myself, what was the original function that when I took its derivative, I got x? So the first question is, what was the exponent of the antiderivative? If the derivative's exponent is 1, what did the antiderivative's exponent have to start off as? Hopefully you deduced that it had to be squared, but if we think that the antiderivative is just x squared, when we take the derivative of that, we get 2x, and that's not the function that we started off with. Remember, we are trying to do the integral of just x dx. So x squared is not a solution to this because when we take the derivative of x squared, we get 2x, not just x. So what needs to be out here in front of the x squared so that when we take the derivative, we get just x and not 2x? That is correct. We need a 1/2. So if f of x, if the antiderivative is 1/2 x squared, then when we take the derivative of that function, we do in fact get x. So the antiderivative of x is x squared over 2 plus c. So we can do a couple more examples of this. Okay, so what if the original function that we are, so let's say we were trying to do this problem. What's the antiderivative of x cubed dx? I'll give you a second to see if you can figure that out. Okay, when you do this, I know that the antiderivative has to be to the 4th power. And I know that I need a coefficient out in front of it so that when I bring down that 4 from the exponent, I end up with a coefficient of just 1 because there was the coefficient in the derivative was just 1. So that means that this needs to be x to the 4th over 4 because when I take the derivative of that, I do get back to x cubed. So what do you think if you had, you're trying to do the integral of x to the 10th. Go ahead and see, dx. Go ahead and see what that one would be. Okay, so then see if you can figure out what the pattern is. If we know what this exponent is going to be, then what does the exponent in the antiderivative need to be, and what do we need to divide by? Ta-da! Here's the answer. So this is just the power rule in reverse. So reverse power rule. When we were using the power rule to take a derivative, we brought the exponent down and decreased it by 1. When we go in reverse, we're going to increase the exponent by 1 and then divide by that exponent. Add 1 to exponent, and then divide by that new exponent. Okay, so here's some examples down here you can look at. This video is going to wrap up. We'll get into some more functions in the next one.